Hi, my name is Edwin Esparza, and welcome to my Rigid Body Dynamics lecture. For today's lecture, we have three learning outcomes. First, we want to understand Euler's equations of motion. We also want to understand when a rigid body is rotating in a stable manner around one of its axes. Lastly, we also want to understand what the intersection of angular momentum and energy surfaces have to do with stable rotational motion. First of all, what is a rigid body? A rigid body does not deform when subjected to external forces. Since the object does not deform, it rotates around one of its axes instead. To describe this motion, we use Euler's equations. This concept is extremely useful since it allows us to treat complex models as a single point, which makes it much easier to predict motion. What exactly are Euler's rigid body equations? Euler's equations are a set of first-order differential equations that can help describe the motion of a rigid body in a three-dimensional space. This is done by relying on Newton's second law. Generally, Euler's equations can describe the rotational motion of a rigid body. This is done by relating the angular momentum and the torque around one of its axes. We can see these general equations down below where N represents torque and L represents our angular momentum. In the case where a body is experiencing rotational motion, our coordinate frame will change based on the angular momentum. This is seen here below. This is convenient to transform from the space-fixed inertial frame, which is this equation here, to the body-fixed frame down here, because the inertia tensor of the rigid body is known. So for simplicity, we will use the second equation. Since we now know that it rotates around one of its axes, we can choose out our principal axes and represent it as the following, where I little I represents the principal moments of inertia. We can now expand and find the components given by the rigid body. Solving through, we get the following components. Now that we have a general understanding of Euler's rigid body equations, we can apply it to a real-life scenario. In this case, we have a tennis racket that is flipped. Using Euler's equations, we can do the following. We can set these general equations of motion equal to zero because there is no torque in this specific scenario. We are also assuming that it rotates mainly around the x1 axis. That means that our omega 2 and omega 3 are small. Rearranging for this, we get Now that we know this, we can analyze the stability using the Jacobian matrix. Keep in mind this is around the x1 axis. We can do so as following. Solving through, we get that the matrix has a trace of 0, and the determinant is as following. As we can clearly see by the determinant, the quantity is positive. Given that it's positive, that means that the solution is growing exponentially. Since it is growing exponentially, that means that our solution is unstable. We can now look at the same example, but this time rotating about a different axis. Rearranging the equations of motion as found above, we get the following. Once again, analyzing by plugging into the Jacobian, we get a trace of 0, and our determinant is as following. Clearly, our determinant is now negative. This means that our equilibrium point is stable. As a key takeaway, if negative, our solutions are stable. This is due to them being oscillatory. If positive, our solutions are unstable as they grow exponentially. Lastly, we want to understand the relationship that the intersection of angular momentum and energy surfaces have to do with stable rotational motion. We know that we can find the energy ellipsoid by taking its general form, and the momentum ellipsoid can be found by taking the magnitude of its vector. Doing so, we get the following. Where this represents the energy ellipsoid, and this represents the momental ellipsoid. Now, we can picture that both of these ellipsoids merge together as one, and we get the picture on the right-hand side. If we take a look at the picture, we can see intersections. That's here and here. These intersections are very important as they represent all possible combinations of angular momentum and energy given at a time. This is where the system is spinning around a stable axis.